Hello, this is Romeo Cat Computers, and I've been designing this calculator out of basic logic circuits. You know, AND gates, OR gates, XOR gates, things like that. And that idea I've been working on for a while now, and the idea got expanded on, and new ideas came out of that, and this is turning into a bigger and bigger project, and I've got other things down the road too. Originally, I was just going to build the calculator and film it and show it off and be done. But I've decided I'm going to start a short little series of videos where I'll not only show off my progress in the calculators I build, but also go into depth on how the logic circuits work. So if you want to build something like this yourself, or you just want to learn how these sorts of things work, then you can follow along with this series, and it might be helpful to you. What I have presented in front of the camera right now is the prototype. It doesn't have all the fancy features, but it's what I've been putting together to make sure that my idea and design and everything actually works. And it does so far. And that's what this video is going to be about. Talking about this circuit and what I built so far. Now before I show you this, I want to show you the overall design so you can see where I'm coming from. This is the overall design. Now what I have is an 8-bit calculator. Although I should say, before you get too confused, this only shows 4 bits, and that's because I drew this up before I decided to go 8-bit. The design is the same, it's just copy and pasted and it would extend out this way. So this is what I plan to do. The heart of it is a chain of 8 full adders. There's also some support components here for extra features and a overflow detection here, but this is the main part. One nice thing about full adders is that if you put some XOR gates on here like so, or if you just invert the B line, the B input lines, you can get it to subtract. And so that's what the XOR gates do. They're basically programmable inverters. So this is both an adder and subtractor calculator. Now the other major part is down here, and this will be programmable memory. Basically, once you have calculated something and it shows on the LEDs over here, you could push one button and it will flash it all to these D latches. And these D latches will output to another set of LEDs. So you could basically have one slot of memory if you really want to save your number. So far what I built now is just this part, not even the subtraction part, just a set of full adders that are conjoined together to allow me to add two 8-bit numbers together to get a 9-bit number. Alright, so now for a tour of the board. This bottom part right here is the control area. There are two 8-bit numbers that you can add together, A plus B, and later A minus B, but not yet. And then a row of 9 LEDs to express the 8-bit value plus the carry-out. And then the carry-in switch, which if you're familiar with full adders, if you're not, I'll talk about it in a future video. Carry-in, in this case, is basically just an extra 1 or 0 you can add. You push it, and it'll add 1. And then these LEDs are unrelated, so ignore them. And then these are all of the logic chips. Now I lay them out in kind of an inefficient design by sorting them by type. So this is my row of AND gates, this is my row of XOR gates, and these are my 2 OR gates up here. And you can see I tried to keep it nice over here, bent the wires and routed them, but after a while I just gave up and made a big haphazard mess. But despite how messy it looks, it does work. So let's turn it on. That's just the basic power indicator. So far we're adding 0 plus 0, so no surprise the output is 0. But let's do some math. I want to add 147 plus 35. Now I've already converted what that is in binary earlier, so all I have to do is type it in. So 147 is this. So right now it's just 147 plus 0 is 147. Or more accurately 0100100011. And now we'll add 35, which is this. So here's our result. Should be 182. And according to the stuff I wrote down earlier, this is indeed correct. 010110110. And of course here's the carry, and I can add a single 1, which doesn't do a whole lot. So now we're up to 183. And now we're at 182. So it works. Now I didn't really go into depth on the logic circuits as I said I would, but this is the beginning early prototype. Once I finish the calculator, I'll talk about the architecture more and some of the techniques I used. But this is basically just a showcase of what I have so far. Now, what is to come? Well, the final board is, if you remember the calculator I assembled a while back out of relays, I put it onto 2 boards, soldered it together, and then basically just mounted it to a piece of wood. That's what I'm going to do here, except it's more complicated, so there's more boards involved, and I'm making it a bit less cluttered. I'm doing it in nice, neat, understandable, modular sections. And so far, at the recording of this video, I've got some of them in the works right now. Not all of them, but here's what I have so far. This is my B-line inverter. The B-line inverter, as discussed before, will invert the B-lines. If you recall, it's got 8 instead of 4. And each of these 74LS86 chips has 4 XOR gates in, so 2 makes 8. So it takes your input here of 8 bits and an output of 8 bits, and then a ground of 5 volts and a signal. Now the signal is basically your selector of whether you want to invert them all or not, i.e. your adder or subtractor mode line. When it's low, it passes everything through as normal. But when it's high, when you're in subtraction mode, everything here gets inverted to here. Hence the B-line inverter. And it's got an LED and a jumbled mess of wires, but I have tested it so far and it works. This is one of those little Radio Shack prototype boards. The other thing that I built, or at least I'm most of the way done on, is this. This is a 4-bit adder. It's half of my calculator. Now so far I've only gotten around to soldering the bottom. The top has not been complete yet. So right now it's a 2-bit adder. But I'm going to build 2 of these boards, combine them together, and get my 8 bits. And as you could tell, this is a lot more digestible and understandable. This is just one 4-bit adder. And you can see I've got these nice little connectors here for your B in and A in and C in, and a power connector and your outputs. Now what's funny about this is that there is a 74LS series chip that does exactly this. That is a 4-bit adder, and it is the 74LS83. And just like how many connectors there are in here, which is 16, it's just a single 16-pin package. This is a little 14, so it's a bit longer. So you may wonder, well, why aren't I just using those instead of manually building it out? Well, one of the reasons, even before I found out about it, is just for fun. I want to have fun and build a full-sized 8-bit calculator out of these chips. In the future, I'll probably look into getting some of those 74LS83s. But if I start consolidating everything into fewer and fewer chips, then it starts to get less entertaining. It's just hooking up a chip and wiring it, and then it just does what you want it to do. I enjoy the challenge, and I enjoy the designing of the circuit, and also just the tomfoolery that is a massive desk-sized calculator that can only add up to 512. So anyway, that's what I have so far, and you'll see this and another one and the rest of this probably in the next video. So I hope you enjoyed this, and I'll see you in the next one.